Hey everyone, welcome back. In this video, we're going to start talking about how to solve our larger systems of linear equations in 3 or more variables. And our focus is going to be on these 3x3 systems of linear equations, although we will discuss briefly the larger cases. And so our guiding example that we're going to work through is this example where we're asked to solve x plus 2y minus 3z equals 9. That's the first equation in our 3x3 system. The second equation is 2x minus y plus 2z is equal to negative 8 that is. And the third equation in our system is negative x plus 3y minus 4z is equal to positive 15. And so we are going to be able to build off our knowledge of solving smaller 2x2 linear systems. That's going to help us figure out how to work with and solve these 3x3 or even larger systems of linear equations. So when we were working with our smaller 2x2 linear systems, we had a graphical interpretation involving lines, and that helped us interpret the geometry of the situations and kind of making sense of those situations, like when we had one solution, no solutions, or infinitely many solutions. And we have some similar but different geometric interpretations going on for our 3x3 larger system as well. The biggest difference in the picture or the geometry is, well, now that we have a third variable, we have a third dimension in our picture as well. And so when we were graphing our linear equations in 2 variables, like y is equal to mx plus b, that just gave us a line in the xy plane. Right? And that line would have like an x-intercept and a y-intercept. And we could connect the line with those 2 dots as well. Well, now that we are in the third dimension, our linear equations are going to look a little bit different. We don't get into it too much in this class. It's discussed in later classes. But the graph of a single linear equation in 3 variables is going to look like what we call a plane. So we have 2 points determine a line, and we have 3 points determine a plane in 3-dimensional space. And technically, a plane is infinitely large, so we can't draw the entire picture of it. But just think of like an infinitely big, flat piece of paper. That is what a plane really is in 3 dimensions. And so we could go on for quite a while discussing how to kind of initially visualize a plane in 3D or how to sketch it using a bunch of lines stitched together. But that's not really the point we want to get at here. We're just trying to learn just enough about this 3-dimensional graphing going on behind the scenes to help us interpret these different situations of when we're going to have like one solution, no solution, or infinitely many solutions. But the main point of this initial little discussion is each one of our equations, just looking at a single equation on its own, the graph of that equation in our 3-dimensional space is going to give us a plane, basically an infinitely big piece of paper that could be angled in some weird orientation, depending on the numbers involved. We're not going to be graphing any of these planes by hand. That's not an objective for this course. We just want to make sense of how these planes can intersect each other, because just like in our 2-variable case, in our 3-variable case, we're still trying to find points of intersection, but now between our 3-dimensional objects instead of our 2-dimensional objects. Well, now that we have this third dimension denoted by this vertical z-axis, our planes have a lot more freedom in how they can move and intersect with each other. So we have a lot more than 3 scenarios, although the outcomes still are going to be the same. We're going to have one solution, no solution, or infinitely many solutions. So in these figures from our OpenStack textbooks, we have 3 planes colored green, red, and blue, kind of corresponding to the 3 equations in our linear system of 3 variables. And in figure A, we can kind of see the best case scenario where our 3 planes intersect each other to form a single point or meet at a single point. That single point of intersection is going to be the single solution x, y, z to our 3x3 system of linear equations. In figure B, we can see another case where we have solutions, but this time it's going to be infinitely many solutions, right? Whenever any 2 planes actually intersect each other, they're always going to form a line of intersection. And so, well, if we just have 2 planes intersecting each other, that gives us a line of intersection with infinitely many points. And if that third plane comes in and intersects the other 2 planes also along that line of intersection, then the line of intersection is containing all the points that are common to our 3 planes. Those are going to be all the points x, y, z that satisfy all three equations in our system. And so in a situation like in figure B, we're actually going to have infinitely many solutions to our system of linear equations in three variables. And so now we can see in our second set of figures the kind of cases, although this is still not all the different possible ways planes can kind of orient and intersect each other, but it's enough to get a sense of the different scenarios. But in the second set of figures, A, B, and C, we can see some of the scenarios in which we will have no solutions to our system of linear equations in three variables. Right, in figure A, we can see any pair of our three planes mutually intersect each other to form a line of intersection, but none of those three lines of intersection actually then intersect each other, so none of the three planes have a point that is common between all three planes. We can only find points that are common between pairs of planes, but to be a solution to our 3x3 system, you gotta be a point in all three of those planes. So in figure A, we can see here that we have no solutions. In figure B, we can see that we have two planes that are parallel to each other, so those two planes never intersect each other, and the whole game is off already, but that third plane intersects both. But that doesn't even matter. That third plane intersecting the other two planes does not create a point that is in all three planes, so we don't have a single solution to our system of equations. And in figure C, we can see the case where our three planes are all parallel to each other, and just like parallel lines, parallel planes never intersect each other, so there's no way we can have a solution to our system in a case like we see in figure C. So we're going to be using some very similar algebraic techniques for our 3x3 systems that we use for our 2x2 systems, but we're going to have to be just a little bit more careful. We're still going to have some of those same kind of indicators, like if we run into 0 equals 0 or 0 equals 12, those will tell us we might have infinitely many or no solutions. The 0 equals 12 already always means no solutions. But if we run into something like 0 equals 0 right away, maybe using two equations in our 3x3 system, we're going to have to be a little bit more careful. We can't say that there are infinitely many solutions in that case, not until we take that third equation into account. We'll look at an example of this at some point, but this is something that could potentially happen in figure A or B here. We can find that line where two of our planes intersect, and that'll look like we have infinitely many solutions, but until we take that third plane or that third equation into account, we aren't really sure if that infinitely many points on that line of intersection between our first two planes actually intersects that third plane at all. So just a heads up, our process is basically going to be the same, but we're going to have to be just a little bit more careful before we claim we have infinitely many solutions. All right, and so our first step in our process for solving one of our larger, more complicated systems like a 3x3 system is the first step is to actually reduce the system to a smaller 2x2 system in a case like this. If we're working with a 4x4 system, first we would reduce it to a 3x3 system, and then a 2x2 system, and go from there. So we can extend this process even for larger systems, but our primary focus is going to be on these 3x3 systems of linear equations. So again, that first step is really just a reduction step, although that is where a lot of the heavy lifting is done. We're going to reduce the system to a smaller 2x2 system, and this is usually done by taking two different pairs in our 3x3 system and eliminating the same variable from each pair. So we take maybe the first and second equation and eliminate x. Using those two equations, that'll leave us a new equation in terms of y and z. And then we take a different pair from our original three equations, so not 1 and 2. We could use 1 and 3 or 2 and 3, eliminate x from that second pair of equations from our original system, and that'll give us a second equation in terms of just y and z. And when we have those two equations in terms of y and z, we will now be in our more familiar 2x2 system. And then once we have those two equations in terms of just y and z, we will have reduced our 3x3 system to a smaller 2x2 system that we're more familiar with and know how to solve. So our second step is then solve that smaller 2x2 system. And so as long as that second step has gone well, we should have been able to take our 2x2 system that we reduced our 3x3 system to and solve it. And by solving our 2x2 system, we should find the value for two of our variables like the y and z value that corresponds to our solution if a single solution exists. And then what do we have to do to finish this problem off? well, we have to go back and find the value of that third remaining variable. And so that fourth step here, I'm putting an asterisk next to because it's very optional. That fourth step that I'm recommending, though, is to check your answer. And really, we're pretty much only going to be able to check our answer if we have a ordered triple x, y, z that we can plug in to all three of our original equations and make sure it satisfies all three of the original equations. We get a true statement out of all three, like 9 equals 9, -8 equals -8, and 15 equals 15. And so the procedure we're using is basically the same procedure we used for the 2x2 systems, but we're going to iterate it and basically run it 2 times through. So let's go ahead and actually put this into practice, see how we solve one of our 3x3 systems. All right, just to make my work a little bit easier to follow, let's go ahead and label our 3 equations in order, equations 1, 2, and 3. And our first task in solving this larger system is to reduce it down to a 2x2 system by taking 2 different pairs of our original 3 equations and eliminating the same variable from each of those pairs. In the earlier description, I said let's go ahead and eliminate x, and I think that's actually the easiest one to do, although it looks like eliminating y might not be too bad as well. But let's go ahead and start by eliminating x using 2 different pairs of our 3 equations. So notice, if we add equations 1 and 3 together, they already have the numbers or coefficients in front of x, the same and opposite in sign, so those x's would cancel each other out. All right, so if we add equation 1 to equation 3, the x's cancel out. We have 2y plus 3y. That gives us 5y. We then have to also add the rest of the terms together. We have -3z plus -4z. That gives us a total of -7z. And then adding up the right-hand side gives us 24. And so let's go ahead and call this equation that we found using equations 1 and 3 that ended up now in terms of just y and z. We'll go ahead and call that equation 4 for future referencing. And so we've used equations 1 and 3 as one of our pairs to eliminate the variable x, and now we need a different pair of our 3 equations to also eliminate the variable of x. And so that means we can't use 1 and 3. We could use 1 and 2 or 2 and 3. It doesn't matter. As long as we use these 2 different pairs, all 3 equations will be involved. And so let's go ahead and use equations 2 and 3. Notice if we take equation 2 and add 2 copies of equation 3 to it, then we'll get the x's eliminated, right? If we multiply equation 3 by 2, it's going to turn into -2x plus 6y minus 8z is equal to 30. That's just 2 times our third equation that I wrote in blue below it. Now we're going to add that to our second equation, and now we can see more clearly that those x's really will cancel each other out. So the resulting equation we get from equation 2 plus 2 times equation 3 is the x's cancel out. We get 5y's. Oh, that's really nice. Then we get 2z minus 8z is -6z. And we have to add the right-hand sides as well. -8 plus 30 is equal to 22. And so by taking these 2 different pairs of our original 3 equations and eliminating the same variable from each pair, we've created equations 4 and 5, which are now a 2-variable system of linear equations in y and z. And so now we can solve this 2x2 system just using our previous methods and find the values of y and z. Notice here that in the reduction step where we reduced our 3x3 system to our 2x2 system, we used that elimination method. We could have also used the substitution method. It's really a preference, although you'll probably see most resources using something like the elimination method because it does become a bit more efficient and easier to follow your work using the elimination method for these larger systems. So now we can notice if we subtract equation 5 from equation 4, or we could do the difference in the opposite order, it doesn't matter. Either way, if we subtract these equations, the terms involving y will cancel each other out. So you have to be careful with distributing this negative though. So we have 5y minus 5y giving us 0y, or canceling out the y's. Then we have -7z minus -6z, or plus 6z. That leaves us a total of -1z, and that's going to be equal to the right-hand side with the difference taken. 24 minus 22 is 2. So solving for that by multiplying both sides by -1, we see that z must be equal to -2. So we aren't finished solving our 2x2 system. We have found z, and now we can use that information and equation 4 or 5, it doesn't matter which. But with one of those equations, we can then go and find y. Let's just go ahead and use equation 4. So equation 4 tells us 5 times our unknown y value minus 7 times our now known z value of -2 has to give us 24. Well, this says 5y plus 14 is equal to 24, or 5y is equal to 10 after subtracting 14 from each side, and then dividing both sides by 5 yields that y must be equal to 2. And so we're not done solving our 3x3 system yet. We're like 2/3 of the way there, because in order to finish solving our system, we need the value of that remaining third variable, that one we eliminated initially, that variable value for x. And so now that we know our value for y and our value for z, we can use any of our earlier equations that also involve x, plug in those y and z values, and then solve for x. I'm going to go ahead and use the first equation just because it already has a single x involved. We won't have to divide by 2 or multiply by -1 as an additional step. So what that first equation tells us is our unknown x value plus 2 times our known y value of 2 minus 3 times our known z value of -2 has to give us 9. So putting that all together, it says x plus 4 plus 6 is equal to 9. Well, 4 plus 6 is 10. And if we subtract 10 from each side, we find that x is equal to -1. And so to wrap this problem up, we just want to write our answer as a nice ordered triple, x, y, z. Our point of intersection between these three planes occurs at the single point where x is -1, y is +2, and z is -2. All right, so just to summarize really quickly, the way we solved this 3x3 system was first taking two different pairs of our original three equations, eliminating the same variable from each pair. In this case, we decided to eliminate x, and that gave us these two equations, what we called equations 4 and 5, in terms of just the remaining variables of y and z. This is just a 2x2 linear system of equations, so we go ahead and solve that using our previous methods. So then we find the values of y and z. Once we know those, we back substitute in our earlier equations involving x to find that last variable, that x value. Once we have x, y, and z, we have solved our system of equations. And so everything worked out really nicely in this example, but that might not always be the case. Sometimes our numbers might involve some gross fractions where we have to use techniques like clearing the denominators. Other times, maybe more than one variable will be eliminated in our elimination step. In that case, that's actually nice. That makes us do less work at the end of the problem. Or we could have a situation where it doesn't work out nicely, where we have like no solutions or infinitely many solutions. Not nicely, I just mean not a nice single point of intersection or a single solution.